Okay, I think we're live.
Are we live? Okay, if we're not live, then it's like kind of their problem because I want to start already. Yeah.
It's live.
Okay, sure, great.
Change the thing. Yes.
Okay, actually I'm not gonna start the slides. I'm just gonna going straight into the KiCad because okay, great. So here's the when you open KiCad, you should see this. Okay, so there's a few files here which I don't think you're gonna have yet because you just started, but basically KiCad KiCad_pro, this is the project file. Okay, and then within the project file you've got backups which nobody cares about, and you've got PCB and schematic. Okay, so the schematic is the graphical representation of how things are electrically connected together, and that's like where most of the circuit design goes in. Okay, and then the PCB is where we actually take the physical arrangement of parts and we arrange and lay out all the traces. Okay, so in a schematic all of your wires are ideal. Alright, they have infinite current capacity, they have zero impedance, whatever. Okay, and then once we go to the PCB design where we do the layout step, that's when all of your wires are suddenly terrible and you need to do something about it. Okay, so you can go jump into the schematic editor and you should see something like this. So you've got this schematic page like this. I've set mine to like A2, which is gigantic. You can just change the size. A4 is the standard, so I'm going to change it to that. Okay, half of my stuff has flown away. This is absolutely
create a new project first.
Did I forget create new project?
Yes.
Okay, sorry. Actually, yeah, I should just create a new project. Why am I like eating into my... Okay, yes. So go to File, go to New Project, and then go and choose a folder that you want to put it in. So I'm going to put it in KiCad Projects because like I've got a folder for it already. Literally any folder is fine. Okay, so then you'll have Pro, PCB, and Schematic.
You should get a form that says if you want to configure it, just click OK. Like configure the default schematic.
What?
Library, default schematic library.
Oh.
Just use the default.
Yeah, just use the default. Don't be a Jedi, just do the normal thing, it's fine. You're eating, right?
Yes. Oh, this fine.
Yeah, okay, jump into the schematic editor for those who can already see it. Should look like this. Everyone good? Is anyone configuring, stuck, anything? Your table okay? Alright. Okay, so there's some stuff at the sides. We'll just quickly touch these first, okay? So I have never touched this in my life and I don't know what it does, so you shouldn't touch it either. This is your default units, okay? So inches is inches, mils is milli inches, is it?
2.54 millimeters.
Oh, mils, okay, so mils is 2.54 millimeters. Don't care. We're in Singapore, so we're gonna use mm, okay, here. Alright, then this is not important. This is probably not important. What else is important? Line. Ah, yes, okay, so you see this tree here, set line mode to the middle one, okay? Horizontal and vertical lines only. This is purely for readability. So basically this is I'll show you later, but like for now just set it to this and just take my word for it. Okay? Yeah. Okay. Annotate automatically should be yes. Hierarchy, navigator, and properties we don't care. Okay? So you care about this. This should be set to this one. Alright, click this, not this, this. Alright, then set to mm for everyone's convenience. Alright? Okay, on top most of it is like a bunch of rubbish, we don't care. For now let's go straight into symbols, alright? So this is highlight nets. Okay, nets is a key concept in PCB design software. Alright? So whenever, so basically a net is a set of positions which are connected together electrically. Okay, so that means that like you have this set of points in your circuit which are all considered to be connected by ideal wires. Alright, and later I'll show you, but like you don't need to wire something together, you can just make them part of the same net, and this makes your circuit way cleaner. Alright, because like the moment you have more than like 50 wires, everything just goes to hell basically, you know. It's much easier to use nets for everything. Alright, okay, so that's highlight nets. Underneath that is place symbols, which the shortcut is A. Okay, so yeah, just place a symbol, like any symbol. Okay, so the by default, like you're just gonna see this big list of stuff. Okay, do not be overwhelmed, everything is fine. Listen to my voice. Okay, let's just put R. Okay, so R is resistor. Okay, and yeah, is everyone able to like get this page? Everyone okay? Right, so this is placing a symbol. Okay, so a symbol like says that there's a resistor here in your schematic, but you can see here that we've also got footprint. So footprint is the actual physical size and shape of the resistor on the PCB. Okay, so we can choose between like many different footprints, and for now just trust me and choose 0603 1608 metric. Okay, and we'll, yeah, it's here. If yes, find a chair anywhere. Here is fine, there is fine. You can take a chair from the back. Yeah. I forgot about the aircon. Yeah. Joseph, this one's mine, is it? Yes. Okay. Okay. So everyone's able to get this, right? Okay. So when I click the footprint, you see that it's got this thing that shows up here. Okay. So this is the physical shape of the resistor. So you see these two red areas. These are the copper pads that the resistor will solder onto. Okay. So basically, there's show you picture. So this is a through-hole resistor. This is what we're used to, right? In all of your breadboarding, you've just got this like big cylinder with two pins coming out of it. So a through-hole resistor means that we have holes physically drilled into the PCB. We put the legs through the holes and then we solder it like a breadboard. But we also have SMD components, which is surface mount devices. Devices, right? Yeah, so this is a surface mount resistor. You can see it's way smaller. And what it basically is, it's a cuboid with copper on either end. Okay, and we take this and we just place it on the PCB, and there's two matching pads, and we just solder the tips directly to the pads like this. So here's the pad, here's the tip. It just solders directly. All right. Let me see if I can find a close-up image. Yeah, so it'll look something like this. All right, and then we solder it onto the pad like that. See? Everyone kind of gets what I'm saying, right? So the footprint, in this case, we are specifying that this is an SMD resistor, so not through hole, because through holes are gigantic, and we are specifying that it's 0603 or 1608, and 0603 is imperial, 1608 is metric, and this basically says what is the size of the box. Okay, 0603 is like a pretty common size, which is why we're using it for now. Ken?
Wait, so this is for the circuit board design, so that when the company gives us a circuit board, they will have like the slot there for us to solder.
Yes. Or also, if you ask them to solder for you, then they will put the resistor there, and it'll be the correct size. Yeah. Okay. All right. So for now, we're just gonna put that, and the footprint has absolutely no bearing on how you put your schematic. But like later when you do the layout, it's good to have the footprint correct in the first place, because you can manually assign footprints later, but that's troublesome. All right. Okay, so this resistor here if I click on it, you can see that there's a bunch of stuff at the bottom which says the properties of the resistor. So the reference R1 says that this is the first resistor in our circuit. Okay, and I can change this to any number as long as it's unique. But basically, when we generate the PCB later, or when we design the PCB layout later, the reference is how we're gonna know which resistor is which. Okay, so in this case, it's just called R1. All right. Then the value right now it just says R, so I can click on that directly, and I can put some number, 10 kilo ohms, like this, 10 kr. All right. So I just double click it and just write here. I just override it with whatever. Okay. So you can have 10 kr, you can 10 milli R, whatever you want. You know, 2.2 kr, sure, whatever. Okay. So this is how we just add a simple resistor. So this is a symbol in the schematic. All right. Okay. Then you can see that we have the library, which in this case is just device. Nobody cares. Then footprint 0603 metric. 0603 1608 metric. Okay. Or just 0603 for short. Alright. Okay, so we can add a resistor like this. We can add other stuff. So I'm gonna go back to my symbol placer, and I can add a capacitor. Capacitor is C. Alright. And again, there are different footprints that you can use. So I'm gonna add 0603 metric again because I might as well. This is fine. So here's a capacitor. Alright. So again, for the capacitor, it's got its own reference designator, which is C1, and this C value is like just nothing right now, so I can change it to something 10 microfarad. That's fine. Okay, for example. All right. Anyone lost? Anyone happy? Anna, great. Okay, so Anthony, how you holding up with no mouse? Can so far, right? So are you able to like zoom in and out and whatever? Okay, great. Alright. So now, so these are just symbols, okay? So let's say I wanted to add power and ground. My circuit needs power and ground, right? So I can go to the next one, which is power symbols, or P for shortcut, and you can add the power symbols. So ground, just search ground and you'll get ground, okay? By default, just use the regular ground, okay? There's like 10 different kinds of ground, but like just don't think about it, okay? Those are for like real engineers to use. Alright, so we'll just put ground here, like this. And then I can also add power, so 5 volts for example, but I'm gonna use 3.3 volts because I want to. Alright, so again, there's 3.3 volts, and then there's all these other funny 3.3 volts. Don't care, okay? Just use this. Okay, these are for like application specific 3.3 volts. It's still 3.3 volts, but it's labeled with a specific application. Like maybe this is like a cleaner, flatter DC or something. So by default, we just use regular 3.3 volts. So we can add it like this into the circuit somewhere. Okay? Okay, so you can see that I placed my ground directly on top of the circle of this capacitor. So this capacitor, the circle basically means that it's a connection point. You can do things to that circle. Okay? So if I connected ground here, it doesn't do anything. Alright? But if I put it here or here onto a circle, then it makes sense. I can also put it in mid-air like this, and I can click the circle and a wire will immediately appear. Okay, alternatively, you can attach a wire with W. So I can click the wire button and like I can go and click circles, and then like I can come and draw wires. Okay, so this is where your wire routing starts to, this is where your line mode matters, okay? So by default, most schematics are just gonna be horizontal and vertical because it's clean and easy to read. But if for some reason you feel a need to be special, then you can like do stuff like this, you know? Which, like, why would you do that? Why? Like, how is anyone else going to read your work now, you know? Why have you wanted your friend to check your work before you spend money on the PCB? So like, just use this and it's way better, okay? There's also this mode where like you can do this, so it's like 45 degrees horizontal and vertical. Again, why? This is a graphical representation of your circuit. The shape of the wires does not matter, okay? So just do the thing which is the cleanest, which is vertical and horizontal, like that, okay? Okay, so I place my ground directly onto the terminal of my capacitor. If I want to, I can now take it and I can drag it around like this. And you can see that because they were already connected, a wire will just interpolate between them. Similarly, I can take my 3.3 volts, which was connected by a wire to begin with, and I can bring it all the way here, and now there's no more wire, but these are still connected to each other. Okay? Any questions? So everyone accepts how like wiring things together works, right? Okay, now to reiterate, this is a schematic. All of these are ideal wires. Okay? So you should not go, oh, look at this long ground, I should add an inductor here now to model the impedance. No, do not do that. Because if you do that, then you are going to go into your PCB and you're going to have an inductor which you also have to place, and no, you've just added more inductance to the thing, right? So we assume these to be ideal wires, and in the PCB layout later, we will just make them as ideal as possible. Okay, you don't need to model the parasitic RLC components on this later, on this right now. Okay, all right. So I've shorted 3.3 volts to ground with a capacitor. This is just a decoupling cap now, right? Okay, so any questions about how to place symbols? Everyone's pretty happy, right? Okay, great. So this is basically what we're gonna be playing with for a while now. All right. So I'm gonna just get rid of these. We are going to jump straight into like hell, and we're going to we're going to start connecting things to an ESP32. Okay. So remember, this is a PCB design course, specifically digital electronics. So our example is going to be where we're gonna make our own ESP32 dev board, and I promise you it's pretty easy. Okay, especially because we already did it for you and you just have to copy. Alright, but if you want to do something else, that's absolutely fine, and we'll just guide you along the way just the same. Okay, it's just that there's like higher chance that it won't work because we haven't checked it. Okay, alright, so I'm going to close this, and I don't care about this, and we are going to jump into my yes. Okay, do not be overwhelmed, just like focus on one thing at a time. This is the application schematic for implementing an ESP32. Okay, so this is the ESP32 here. We're going to add this symbol to our schematic. Alright, so I'm going to take this whole thing and I'm going to copy it for reference, but like we're not going to use it. It's just for me to refer to later. Okay, I'm going to put it outside the sheet so that we don't stare at it too much. Okay, alright, so we're back here in our now empty schematic sheet. Go to symbols and search ESP32. So an ESP32 is a microcontroller, okay? And a microcontroller basically, it runs code on itself, and you can use the code to control the digital pins. And we have a whole lesson on microcontrollers later. Alright, but for now we're just gonna talk about how to connect it up. Okay, fair enough? Alright, so here's the ESP32 S3 Room 1. This is the one that we're gonna be using today. Okay? So search for this exact one. Alright, because our application schematic won't work for the others. You can use the default footprint, which is just this. Alright? Yeah, just type that S3, that's absolutely fine. Yeah, there you go.
It's also
S23.
That's true.
No, this is not like Samsung, it's my expressive.
That's the one.
There's no S23. Is there?
Yes.
There's no S23, right? Cannot be.
The Soul Challenge, the first
S3,
I think someone lied to you.
Yeah.
No.
No, someone scammed you. There's no way.
Because it was 3, 2, and then 3.
It's just like when
3,
you
2, and
design a
then
product, you can sign like
Yeah, just help.
then
I think it's like 328.
like model name lah. Then
It's
just
323, not 328.
S3
there was ESP32 and then like S something.
S3.
Okay, guys. Everyone able to place the symbol, right?
Yeah.
Okay, so I'm starting with a clean schematic. All right. I trust that you're gonna do the same. And okay, so this symbol is quite complicated. It's got a lot of things going on. All right. This is fine. Do not panic. So you can see here that we've got all of these circles. Again, these circles are what we can connect things to. If you try and connect a wire to like mid-air, it won't really let you. You know, this is like, it just like spawns like new places basically. And once I escape or enter, it's just gonna disappear. Oh wait, if you do it the other way, it works.
What?
Wow, if I start from air and then go to the symbol, then I can place a... Okay, I didn't know that. Okay, fine. Alright, so instead of placing... So, here, this is called a net label. This. Alright, so you can see that I've got all these words which are just wired to my ESP32. And these are called net labels. So whenever we take something and we wire it to something else, for example, I put a resistor here, and I wire this to this. Now, this pin and this pin are part of the same net. So a net means that they are wired together by ideal wires, which is this. Okay? But look at this thing, there's like 40 pins on it. So if I just wire everything out, it'll look like a disaster, right? So instead of doing that, what I can do is I can go to this underlined letter A. Place net label. So we can place net label, and then it asks us, what is the label? And then I can say, oh, it's IO39, you know, or whatever. You can type basically anything in here. And then I place, look at that, see? Here's IO39, and I can wire this to this. Alternatively, I can just like place it directly on the pin, which can be cleaner sometimes. Alright? Cleaner just means more readable. Then I take this and I do this, and now look, my resistor is connected to IO39. So this will cause the software to accept that this is connected by an ideal wire, even though I didn't explicitly draw a wire out. And this makes complicated schematics much more readable. Okay? So this point is connected to this point. That's it. That's what net labels do. Okay? Yes, it's very convenient. So if you want to do this, for other things, just have a differently named net label, and then the net will be labeled something else. Okay? So whenever we place a net label, we are spawning a net, which says, you know, now I am a set of things which are connected to each other. And then you just add more and more things to that set as you continue. Okay? Of course, sometimes wires are still cleaner. For example, you look at my application schematic, it's very clear how this is wired up. If I just did net labels for these, then like I could place these like anywhere, and then like people wouldn't even know that this capacitor existed. Right? So having wires graphically like draws the thing together, and that makes it readable sometimes. But if I had like 1,000 wires coming out of this thing, then I would just die. So like we use net labels for things which are very repetitive, or like when there's a lot of them near to each other. Make sense? Yes. So we do all the connections to like the little circles here. All right. Okay. Any questions about net labels? Yeah. If you have only a few wires, you don't have to use net labels. Okay. Net labels are just a readability thing. Yes, you can wire as many as you want into the same net. A net is just a set. Okay. Infinitely big. Yeah.
Where did you put your like sticky chip? Nets, like other parts like in the
You put them wherever you want. However it makes sense, you know. So like if you just make this fly away like somewhere here, and then like you have a bunch of stuff in between, then like someone reading your schematic is not going to assume that this is in any way related to this. You know? So like schematic readability is important. You try and put related things close together. And ideally you like box them up like this. This is just a blue box which I graphically draw. Okay, so Hangi asked a question, is like, yes, I net label together, now where do I put this? Because this can go anywhere, right? So my answer is, keep the schematic readable. Alright, so for example, you look at this. This is the USB port for the ESP32. Alright, and what I want to show you is this blue box, which I have labeled. So you can actually label things or group them together. So I can just draw a box around anything. This box is purely a drawing. It does not affect the schematic at all. It's purely for the user to look at. You know, so I can box this and then I can label it like that, right? Or I can go to the T button down here, draw text. I can just type anything and just put it here. Or anywhere really. I can literally put this anywhere. So you can see all this blue text which I have. These are notes to myself. So as I read the datasheet of a part, I go, look at this. This seems important. I just write it on my schematic. Okay, so this is good practice for when you're starting to learn and you're like not sure what's going on. Sometimes you cannot recognize something just because of the way it is, right? So like you put notes to yourself. So that's what this blue stuff is for. Okay, these are notes for yourself. You can also change the size of them. So what's the text size? I can put whatever I want. Okay. So I can make this 3, and then it'll be gigantic. Or I can change it back, you know. So annotate your schematic properly and group related things together so that people will look at it and be like, ah, yes, this is related. Because it's very annoying if you have to read every single net label. What if you have 1,000 net labels, you know? Then at some point you start to lose track of everything again. Yeah. Okay, so any questions about net labels? Anyone okay? Okay, good. I'm gonna delete this now because I didn't need it. Alright, so we're gonna start by wiring power and ground. Alright, this is quite a reasonable thing to do. So to wire power and ground, go to power symbols and add ground. Here is ground, just put it here, no problem. And then do the same for power. So get 3.3 volts and add it here. Okay, great. Now immediately we have a problem. Remember how we talked for like 20 minutes about decoupling capacitors last lesson? Yes, so let's add some decoupling capacitors. So I'll just drag the 3.3 volts higher and I'll add some decoupling capacitors. So for now I'm just going to assume that this footprint is okay, but in reality this is bad practice. So what you should, whenever you choose a part, what you should do is look at your fabricator. Fabricator is the company who's going to manufacture your part. If you're gonna, like, even if you're going, okay, so basically, yes, the part is here in the software, but is it like procurable in real life, you know? You have to shop for the thing first, otherwise you're gonna use it in your circuit and then like realize later that you don't know how to buy it. So by default, we go to JLC PCB because like for whatever reason everyone in SUTD uses JLC PCB. Okay, they're very good, but like, I don't know why, like because other manufacturers are good too, right? So like, I don't know.
They use PCB way also, but they're not.
Yeah. So you can go to JLC PCB SMT parts library. So literally go here, JLC PCB SMT parts library. Go to this. Alright. You can click it and then now you can search for your parts. Alright. So this is a huge library of parts which the fabricator has available. And if you want them to solder the board for you, they better have it available, right? So then we can search for capacitor 10UF or something, you know, and then see what sizes they have available. So in this case they have like all of these sizes available, so we should be fine, you know. Package type means the size. Alright, there's only so small that you can make a capacitor because like you have to fit a certain amount of plate inside the capacitor, right? In order to achieve a certain capacitance. So there's a minimum volume for a capacitor, and the bigger the capacitance is, the bigger the capacitor needs to be for a given voltage rating. Does this make sense? Yeah, exactly. So just check if it exists. Wow, they're all out of stock. This is amazing. So you can check if OA05, which is the next bigger size, exists. Wow, they're all out of stock. What the fuck? 1206. My goodness. Okay, reset all. Am I dumb? It's just a capacitor, bro. Why is everything not happy? Not through hole. Yeah. MLCCs. There we go. Okay, so I filtered it to ceramic capacitor, which is what we normally use. Alright. So then you can see, look, I've got 10 microfarad capacitor. I'm gonna zoom in for you guys. So here's a 10 microfarad capacitor, which is what I was looking for. It's rated for 16 volts. Is that a through-hole capacitor? It is. I've been lied to. Where's my SMT capacitors?
You use a search bar?
I always use the search bar. What do you use? Oh, you go into the specific.
Yes.
I forgot. Yeah, okay, fine. My bad. Go to MLCCs.
That's the wrong one again.
Why? Because it's
It's
leaded.
leaded.
Who cares about leaded though?
There's SMT one as well.
This is
It's right
terrible.
next to it.
This is terrible. Yeah, okay, fine. So go in here and then you can search for the capacitor. So in this case, I want microfarad. I want 10 microfarad. This. Go for basic parts if you can. So JLC PCB splits parts into basic and extended. Basic parts are cheaper. Get the basic parts, alright? Only if you cannot find it in basic, then you get extended. Okay, I know I confused everyone just now. Who doesn't understand what's going on? Is everyone okay? Yeah, we're learning how to shop for the parts, okay? Because if the part is not available, then you shouldn't use it. Yeah. So find search for the component you want, and then like make sure it's in stock, and ideally it's basic, and then you apply the filters. Oh, wonderful! They have like 2 million. We are fine. How big is it? 1206, 0805. Okay, so we can go. So 0603 exists. We'll just use 0603 for now. Okay. So you can see here 0603. 10 UF. This is what we wanted. Alright, okay, so now we can go back. I can choose 0603 safely. So this is an 0603 capacitor. I know it exists. Okay? Everyone happy?
It should always exist.
I mean, it depends. Like, sometimes you get a huge capacitance and then you don't check, and then it's like, it does not exist in the package size you wanted, you know?
Yeah, I mean, it's always safe to use 0805 for.
Yeah, I agree. Okay, so then we can place our capacitor here. And I've been fighting so hard for 10 UF. I'm gonna put 10 UF here. Okay, so this is my decoupling capacitor. Now we need to wire it up. This side goes to 10. This side goes to 3.3 volts, and this side goes to ground. This is a standard decoupling capacitor. Okay, 10 UF is actually quite big, but it's fine. Never mind, I have 22 UF here. It's even bigger. Then I want another capacitor here. So this big one is going to be the bulk capacitor, which is near the power supply, and this is going to be the small one, which is nearer to the IC. I'm gonna put 100 nanofarad. That's probably fine. Okay, and then we can just wire these together like that. Have I lost anyone? Okay, take note that when you copy a capacitor like what I did, the footprint will carry over. So look, I'm gonna copy it again. See, the footprint carries over as well. Alright, so all of the properties carry over, and then you need to manually change whatever you need to change. Okay, you can also just add C from the component library again. Is everyone okay?
Wait, why do you have the smaller one outside? Shouldn't the smaller one be inside?
Doesn't matter, it's connected the same. Doesn't matter.
Also, don't you have to check if the second one exists?
No, because this one's smaller than this one, so it confirmed exists.
So like
Cause like you can only pack so much capacitors into a certain size, right? But I've already verified that I can check this. I've already verified that I can pack this much in. This one's smaller. Like this one is smaller, so it confirmed fits as well.
You're asking about whether you can find it.
yeah, I mean,
You can do the same thing.
Yeah, you can do the same thing. In this case, I know that it exists. Yeah.
The more you design PCBs, the more you'll know what exists.
Yeah. But for all your first times, just check, you know.
Yes.
Okay, any questions? So later you can either go to properties. No, not properties, sorry. That's the painful way to do it. Go to assign footprints. So assign footprints is up here. Okay guys, question. How do you change the footprint later? So go to assign footprints, it's up here, okay? Fourth from the right. Unless your toolbar is different from mine for some reason. Then come here and you see all of your components. It's here. Assign footprints. Click it, go in. You got this whole list of all your components with all the designators. Why is the list different? Okay, so find the component designator that you wanted. Let's say I wanted to change C20. Okay, then you can find what it will appear in like this big list. You can go and search for related ones in here, or you can search in the search bar up top. Can? So maybe I want 0805. This is fine. Then like it'll filter everything that's 0805 in the name, and then I can choose this 0805, and then like I can apply and continue. You have to apply. Okay, don't just press OK. Can?
I take assign footprints to send me the annotated file. It's a bit fast, sorry.
Okay, Hangi got sent to a pop-up window that says annotate please. Just press annotate, it's fine. Okay. Everyone okay?
I really don't know what it was so far.
We're gonna use it later. Yeah. Okay, cool. You might want to pull this a bit out just like. Okay, so whenever you have like anything which is gonna draw power at random irregular times, it's usually a good idea to put a decoupling capacitor. It doesn't really cost anything. It costs a little bit of board space, but like I don't know how many of you guys are making super tiny PCBs, so it's probably fine, you know. So just add decoupling capacitor if you're not sure. Alright? Check datasheet also. Sometimes it makes things worse. But rarely. Okay, the ESP32 has an enable pin. So this is the enable pin. So it needs to be high in order for the thing to like turn on and start working. So I'm not gonna make you read the datasheet, but basically the ESP32S3 datasheet says that the enable pin needs to be turned to high like after like 100 milliseconds after we apply power to this thing. So that means that we cannot just short this to 3.3 volts and call it a day, because it will turn on at the same time. Okay, so we add an RC delay, which we talked about last lesson. Okay, so this is what an RC delay looks like. See, I put a note to myself from the schematic, this is from the datasheet. Alright, so whenever you look at the datasheet and you're like, this seems important, just add it to the schematic, okay? Again, I'm not gonna make you read the datasheet because it's painful. I'm literally gonna copy this, but for you need to add it yourself. Okay, this is a 1 UF capacitor and a 10 kilo ohm resistor. And just wire it up by yourself. Notice how my capacitor is like a different orientation than yours. You can use the rotate buttons up here in order to make that happen. See, I can rotate it like this, back and forth. Okay? Can? You can also take something and mirror it like this with the mirror buttons. Okay? Any questions?
This is for a time delay, right?
Yeah, so this is a time delay. It's okay, just learn how to use it. Once I go in Google.
Press R.
By the way, what's ground actually like?
Ground is 0 volts.
Voltage is between 2 points, right? So it's always like from some point to some other reference point, right? So ground is a reference point in the circuit which we define to be 0 volts. Okay guys, something to clarify. 3.3 volt and ground, these are also nets. Okay? They are nets which are specifically for power, not for signals. And hence they are given their own power symbols. Alright? Do not use regular net labels for power symbols. I will show you why later. But basically, when your schematic gets really complicated, you will start splitting it into multiple sheets. And regular net labels do not cross over into different sheets. So
There are global labels.
you can use global labels lah, but I'd rather you just use the power label, which is for power, you know, like it makes it more readable. Can? Yeah. Yeah. Ground and what?
No, ground is always 0 volts. Negative can, let's say you put your ground at 3.3, then your negative is negative 3.3. If it's a battery, if it's a 3.3 volt battery, you get what I mean? Basically, negative doesn't mean ground.
Okay.
Yeah. Negative doesn't mean ground.
All that matters in a circuit is that there's a place of high potential and a place of low potential. Current flows from high potential to low potential, right? There's like 0 potential is whatever the hell I want. So like 0 potential can be like some value, and then like both my voltages can be negative. It doesn't matter. All that matters is that one is higher and one is lower. By default, we say that ground is 0 volts. Okay, and then like everything else is like 3.35 volts. Because this is convenient, because then I can see what the potential difference is, because ground is 0. Because The difference between 3.3 and 0 is just 3.3, right? Which is my potential difference, right? If I put 100 and 100 and 3.3, then like the circuit works exactly the same. Nobody cares. There's no difference in the physics. But then now I have to actually subtract things. Isn't that annoying?
So negative is just like what you define to be the low position.
Correct.
Correct.
Yeah.
So let's say this is 3 volts. Then I specify this is ground. Even though this is the negative side, this would be just negative 3 volts. This point.
Yeah, it doesn't matter.
Doesn't matter.
Okay, it's all about potential difference.
It's all about where you define it to.
Yeah.
But you cannot do this lah. You cannot do this lah. Then this will not make sense lah. This will be a short. You are shorting the battery together. This will not make sense.
Because now he's added ground to both sides of the battery.
So like this is basically connected already. This is basically connected. It's the same thing.
Ground is a net, right? So everything in ground is shorted together by ideal wires.
Yeah.
So you shorted the battery.
Yeah, basically. So everything that's ground is connected together. And everything that's 3.3 volts is also connected together. Yeah, that's how it works.
Also, actually, we're connecting like the capacitors all to the same point.
Yes. Okay, so does everyone understand what we were talking about just now?
Wait. When you said power is a net, the 3.3 volt is also a net?
Yes.
Oh, so it's all coming from the same place?
Yes.
Oh. Oh, okay.
Yeah.
Okay.
So that means this is connected to this.
Oh.
These two are connected.
Yeah.
And this is connected to this.
Oh.
So there's, imagine a wire connecting from here to here. But
Like-
if you want to connect from here to here, it'll be messy lah.
Or at least it can get messy once I've got
get
like
messy.
once I've got like 10 3.3 volts all over my circuit.
Yeah.
Fair enough.
But wait, will this ever create any interference like with each other because since they're all connected together?
We talk about that later. Yeah. The answer is like, yeah, I guess. But like also like just wire it better, bro. You know? Yeah. Okay. Like for now we're just doing schematic. We don't care about interference. We don't care about like crosstalk between wires. We don't care about non-ideal wires. Right now we just want to connect things that are supposed to be connected together. And then later when we go to like real life, when we actually design the PCB layout, then like suddenly all of your wires are not ideal. Then you have to do something about that. But that's during the layout stage. For now it's just schematic. Okay, so any questions about what we've done so far? We're all okay, right? Everyone's happy? Power is a net, ground is a net, everything is a net. Everything in schematics is by nets, okay? And in layout you also realize everything is by net, okay? And remember, net just means a set of points which are connected together. No problem, okay? Okay, so this is kind of complicated. Alright, but we need this in order to make the ESP32 work. This is a USB port, okay? So I want you to find the USB port. So go into the symbol editor, the symbol placer, and go and find USB B micro, okay? And did I use a custom footprint for this? I might. Is that not custom?
No, it seems like standard.
Okay, then we're fine. Okay, go and find the symbol for this. Okay, it should look something like that. All right. It's got 6 pins on it. See, 1, 2, 3, 4, 5, 6. All right, go and find this. Huh? No. Use the footprint that I have shown here. USB micro B, GTC whatever. Yeah. Is there any way for me to like zoom in on the? Okay, never mind. Maybe I can show. Oh my god! How do I make this like easier to see?
Go to the footprint signing tool. Footprint sign.
Footprint sign.
Click the USB micro J2. And then this symbol.
Big.
Next one.
Yeah. Okay. Use this footprint. USB micro B GTC blah blah blah. Okay. Yes, I apologize for like the pain of finding footprint, but unfortunately the pain of finding footprint is like 50% of the pain of designing PCB. Okay, you just have to get used to it. Huh? Penny Penny has shown me how, so we will move to Type C whenever I feel like it. But for now, we are going to continue building flag operators with micro B.
Type C is moderately more annoying throughout.
What's the difference there between?
Type B is like the directional one with like 2 little spikes at the bottom, the small one. Yeah. The one which like all cheap things use, you know.
Yeah.
But we're building cheap things, so it's fine. Yeah.
Wait, your rocket is cheap?
Huh?
Are you using this for your rocket?
I mean yes lah, but it's fine, you know, like it still works, bro. You know.
As long as it shows up.
Yeah. Okay, has anyone managed to find the footprint yet? You found it? He found it already? Does it look about the same, Joseph?
Yeah.
Okay, great. So that means anyone else should be able to find it as well. You want it right?
This-
No, that's the symbol. Where's the footprint? Show me the footprint.
Oh, right. Yeah, footprint. Oops.
Yeah.
I forgot.
Okay, guys, I'm gonna show you how. Okay. So imagine so let's say I take a symbol, USB micro. Come on. Yes. Why do I have default footprints and you don't?
I do. It's just not, I think it was clicking.
Oh, okay. Yeah, so then go to the footprints drop down and scroll all the way down until you see it. I can't believe. Oh, it's here. Yes. Okay. And then just place it like this. Alright? And for now, I don't care where you place it.
Why can't you? No, it was ground. What? Oh, what? Oh, I thought I could scroll down. I thought there was more than just this. Oops, didn't see this. Yeah, my brain is not braining games. How do you? Wait, hang on. What's the footprint again? Exactly. Like No, I know, but what does it do? Like?
Show you up. Like what it will look like. This is just a symbol. You can see the pads and the layout of the shape. So this whole thing is just a symbol.
So like, it's like to tell the company that's making this like what to put there.
Yeah, correct. This is a footprint. This is a chip.
This is a symbol. Symbol is a thing. Symbol does not represent footprint.
Yeah, so simple is like how does that
Guys, is anyone stuck?
okay.
Has anyone found the symbol?
Exactly. Yes, but exactly what can you put there?
Yes.
The footprint. But like here we just say, we have a capacitor here.
And what
Okay, guys, I'm gonna illustrate what a footprint is because like I can hear people talking about it. But like, okay, so we're gonna abandon schematic for a little while, okay? And I'm gonna switch to PCB editor now. Alright? So this is the PCB editor. It's like dark mode version, okay, to show you that like shit's getting real. Alright? And go to tools and go to update PCB from schematic, the very first option. Can? Is everyone able to find this?
Okay.
Yeah, so it imports all the footprints, alright? So press update PCB, and if it doesn't work, let me know, but like it should work. And then go to close. Then just place wherever.
How do I add the footprint halfway through all these things?
Okay guys, by the way, I got more shit than you because I added an entire like application schematic at the side for my own self to reference, okay? So like I've got more stuff than you. Don't worry about it. Okay, you are fine. Alright? Okay, so check it out. I'm gonna zoom in. Look, this is an ESP32, right? And look at all of my net labels. So all of my pads have the individual net labels on them. Okay? So this is from my schematic. This is my ESP. This is my micro B connector, right? So you can see this is the footprint of it. So this is what the actual physical shape of it is when you put it on the board. So what we're doing now is we're arranging stuff on the board, right? Okay, look at these lines. We call this rat's nest. So rat's nest, like rat like the mouse, and then nest like bird nest. Okay, so rat nest basically is a visual representation of how things are connected together. So I can move this around and you can see the rat's nest moving around as well. So this visually represents what we haven't routed yet. So right now we haven't connected anything, so everything's just connected by rat's nest. Rat's nest doesn't actually electrically connect things. It just tells you, hey bro, you didn't connect this yet. That's what that does, okay?
So the blue lines are there.
Yeah, these lines, okay? Now, I can go to the 3D viewer, and I can actually stare at my PCB. So, you might not be able to do this because I set out all the 3D models already. But like basically, I'm just showing you, look, like this is how it will look like when all the components are placed. So you can see here's my SMD capacitor, and here's the pad that it was mounted on. So then we solder it to the pad, right? So this is the importance of footprints. If your footprint is wrong, then like my chip does not actually have pads to solder onto, then like how am I supposed to build the board, right? That's what the footprint is, okay? And it's important that we care about footprints early, because if we don't, then we're gonna like get to trying to route the board and realize that we don't know what we're doing. Fair enough? Any questions? Oh, so it's here. 3D viewer.
6 from the right.
Yeah, 6 from the right. And you just click it and it should render. And you can free orbit around like in Fusion 360. Can? Okay, I'm gonna delete everything and like leave because like I don't want to. Yeah, discard changes. Okay, I hope that was clear. Okay, I want to be very clear right now. Okay, you're gonna feel a bit lost when we route the USB line, and that's absolutely fine because like nearly everyone feels lost when they're routing USB lines. Okay, like this is perfectly normal. Like look at the amount of nodes I have just for the USB line. All right, it's fine. Okay, don't think too much about it. What I care about is that we've got the USB D- and D+ lines here. Okay, and these need to route to D+ and D- on this. We're gonna use net labels because it's easier. So let's add a net label. And I'm just gonna call it D+. And now I have a net label. Okay? I'm gonna copy it with Ctrl+C, Ctrl+V. This works absolutely fine. You can do Ctrl+X as well for cut. I don't know what Mac users will use. Maybe Joseph can help you. Oh, okay, sure.
Control is replaced with command and alt is replaced with control. Yes. I'm serious.
Okay, so you can't only have one net label because that's useless, right? You want to connect at least 2 points to like make it be worth something. So I'm just gonna add the net labels here as well. Alright? And then we can wire them up like this. You can just drag them so that they intersect, or you can like actually wire them. It's both the same thing. Okay? So now I have D- connected to D- here. And I can highlight nets. See? So look at that. I'm highlighting everything in a net using the first button. The second button. Highlight net. So I can escape to stop. I can go back. I can highlight the net like this. So this will highlight everything which is connected together. Oh, okay. Okay, is everyone able to like spawn the net labels?
Yeah.
D+ and D-, right? It's just a text label which says, look, I'm part of this net called D+. underscore A is the net label button. Apparently L is the shortcut.
How is it actually on the schema? Just
Hmm?
like, how is it on actual PC? How is that implemented on actual PC?
Oh, like when you do the layout later? I will show you later. Yeah. We'll be getting to that like right after this actually, because like this is the bare minimum to make the thing work. You need a programming port, you need like the decoupling caps and the enable pin. Okay? I think. Oh, we need 2 more resistors, it's fine. Yeah. Okay guys, is everyone able to get their net labels and like connect them up? Is anyone lost? Does like your schematic not look the same, or like you're not sure why something is missing? Okay, good, right? Yeah. 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 You just match links to the pin name. Yeah, okay. CBN good, right? Yeah. Okay, great. Okay, great. So I was showing you the highlight net function. So it's easier to, so it's annoying to like read all of your net labels, especially when you got as many as I do. So you can click a single net label and you can go to highlight nets. So highlight net and then click it and it will highlight all of them blue. Okay, so I can do this for like literally any net. I just escaped to stop doing it. Here's 3.3 volts. So it highlights the wires as well. Okay, so anything connected to these wires are shorted together with the same net.
One wire.
Huh?
Everything else connected.
A net is,
Like everything connected to a singular wire.
yeah. That's basically what you're saying. Okay, but don't worry about the shape of it. Okay, it's a set of points which are connected together. The way you connect it later, like that topology, that's done in PCB layout. Okay, everyone's happy?
Also, the two 3.3s don't connect to like 2 different 3.3.
No, it's all shorted together because they have the same net name,
Oh.
right? Yeah.
If let's say you do one there, if you do one two separate, then just name it 3.32 or something.
Yeah, some funny thing like that, you know. So sometimes we do that. Okay, so sometimes on circuits with like digital and analog signals, maybe you will have a different power supply for digital and analog, because analog will have will need a cleaner DC input. So then you would name this 3.3 volt A or something for analog, you know, and then like now they would be part of different nets. Okay, but usually, at least for digital electronics, we only have one power supply, so it's fine. Okay, sometimes you can have like plus 5 volts here, and then of course like these are both positive, but like one is different from the other. Now these are no longer part of the same net.
Yeah, you can try like that.
Yeah, like that. See, they're not part of the same net anymore. In this case, everything's on 3.3, so we're good. Okay. Okay, so we've connected this to this. This is fine. I want to show you this. Okay, wait. Let's connect ground first. Where's ground? Here's ground. Connect ground to pin 5. Okay. So all of your pins on your symbols should be labeled, so you should be okay. All right. If they're not labeled, then you stare at the pin number and you stare at the data sheet and you're like, ah, yes, I wonder which pin is which. You know. Usually you're fine. Usually it's labeled. Okay. If not, you can import the symbol from somewhere which you like. Usually, like the manufacturer will have the symbol. You can like get it from them. Maybe I'll show you that later. Okay, so ground. Okay, guys, V-bus. V-bus is a different power supply from. I'm just gonna do this. V-bus. Okay, so in the next lesson, we are going to talk about how to power the board. Okay, so basically, USB by default has 5 volts and ground on it, but the ESP32 needs 3.3 volts. So how do we go from 5 volts to 3.3 volts? How do we wire that properly? Okay, so we're gonna show you that in like the next lesson. Okay, that's all about power. But for this lesson, just accept that there's a net called VBus, or if you want, you can label it 5 volts, and it magically becomes 3.3 volts at some point in the circuit. And we're gonna connect these two like with some kind of regulator or something in the next lesson. For now, we just put a VBus here. Can? Okay, great. shield and ID. Henny, should shield be grounded? Yesn't. Yes. Okay, I'm gonna.
Usually say yes.
Okay, it's not grounded on any of the flight computers. Okay, so it's not. Okay, so if you don't want to use a pin on a schematic, you can leave it floating like this. So floating means not connected to anything. Alternatively, you can press Q and put a cross there. So a cross is a no connect flag. The button is here. Place no connect flag. No connect flags do absolutely nothing. Okay, what they do is indicate very clearly in the schematic, bro, this is not meant to be connected. Okay, so maybe like you wire.
The KiCad won't complain it's not connected.
Yeah. So KiCad won't be like, hey bro, why didn't you connect this? You know, it'll just accept that it's supposed to be not connected. For me, it helps me because like sometimes I accidentally delete a wire, so I'm not gonna like worry about whether there was a wire on this circle. You know, I know that yeah, there wasn't supposed to be a wire there. Everything is fine. Okay, so you can place a no connect flag. It's more of good practice than like a strict thing that you need to do, but it's cleaner, so just do it if you can. Okay, in this case we haven't done anything with these yet, but we plan to do something with all these pins at some point, so don't connect them. But take a look at this. PS RAM, these 3 pins, 35, 36, 37. For reasons which are explained very clearly in the data sheet and which I am not able to clearly explain, you cannot use these 3 pins on the ESP32. So let's press Q and let's like close all these pins off so that we remember not to use them. Okay? Alas. Okay, have I lost anyone? 35, 36, 37. Okay, so there's 3 in a row. Yeah. The reason why you can't use them is something along the lines of like, oh, these I/O pins are being used to communicate with the chip's internal memory.
Yeah.
So like, if you touch them, then you're going to be interfering with the chip's ability to talk to its own memory. And then I was like, why did you expose them in the first place? Okay, okay, so any questions? We're just placing no connect flags, okay? Okay, so now all 6 pins on our USB port have been assigned to some kind of net, or we know that it's not supposed to be used for anything, so we're fine. I'm just gonna drag this to look a bit like a bit less bad. Okay, any questions so far? Is everyone alright? Okay, good. What else am I supposed to do? Yes, everything else is like RF reasons. Do we care? The ESD and the impedance matching. Just put it right. Okay. We are about to do some stuff. It's very simple, but like the reasons are arcane and weird. Okay, let's place a resistor. I'm gonna put an 0603 because I like 0603. It's common and it's normal. Okay, I want to put 22 ohms like this. Everyone able to place the resistor, right? Everyone okay? Okay, so when you place R in the symbol placer, in the symbol placing wizard here, then it will just give you a resistor. But if you're not placing a symbol actively, if you're just in like cursor mode or something, then when you click something and press R, it will rotate it by 90 degrees. Happy? You can also like, I mean in this case it's a resistor, nothing happens, but for something like the entire USB, then it will rotate a bit more interestingly, you know? Okay, so...
Wait, you talk about flipping yet?
Yeah, I told them about flipping.
Okay.
I mean, I'll reiterate. We can also flip things vertically and horizontally. Yeah, you can flip the whole thing if you want. Like, for all the good it'll do you, you know? Okay, so... I want to add a series resistor between the USB port and the D- and D+. Okay, check it out, bro. I can take the resistor and I can just drag it onto the wire and it just works. Wonderful. I'm gonna repeat that, okay, just to like show you. Wow, it just works. Yeah, so I can pull this out a little bit. Okay, so I need another one on D+, like this. Okay, now if you want, oh my god, don't do that. You can just select the text and move it. Yeah. So if you select the entire symbol, the whole thing will move together. But if you select just the text, then you can move just the text if you wish. Don't delete the text. Keep the text, but like move it somewhere that's like more readable. Or you can rearrange your schematic so that all the text is visible and like not overlapping if you wish. Okay? So in this case, see how I place one ahead of the other? Okay guys, take note, right? Look at this. I put 22 ohms with a tolerance and a wattage. This is weird. Okay, people don't normally do that. There's nothing explicitly wrong with it, but like usually you don't specify this in the value of the resistor. Okay, by right, like if I'm not wrong, the correct practice is to like put it in a note at the side, plus minus 5%, 0.1 watt. So you would do this, and then this would just be 22R. That's like, I have been told that that is like more correct. Okay, but we are students, so we can get away with anything, right? So just do whatever. Alright, in this case I chose I put this as a note to myself because of this reason. So okay, bear with me, I will attempt to explain the reason. If you do not get it, it's absolutely okay. Okay, now the USB line is a differential line. Differential line is a scary word in electronics, but it basically means that like when this has a positive voltage, this has a negative voltage, and the difference between the two voltages is what my signal is. Okay, so normally when you have a binary signal, it'll be high and low, right? So it'll be, the line will just be at 3.3 or at 0, for example. But here in a differential line, which is a pair of lines, we care about not the exact voltages, but the difference between them. Okay, and this is good because I route the differential pair right next to each other, and if I apply some external EMI to the thing, then both of the voltages will rise, right? Will not affect my signal because the difference between them is the same. This is what a differential pair is. So USB is probably the most famous example of a differential pair. Alright, it's like not, it's very immune to interference as long as you route it properly. And later during layout, I will show you how to route it properly, and then we shall never speak of it again. Okay, but the differential pair is supposed to have an impedance of exactly 90 ohms for USB. So remember, impedance is the resistance against current due to parasitic R, L, and C. Right? Does this make sense to everyone? So we need it to be 90 ohms exactly. Sure, bro. That's what the specification says. We just follow. Okay? So it so happens that these particular pins, USB, D- and D+, according to somewhere in the ESP32 datasheet, which I don't remember where to find it because it's like 3,000 pages, somewhere it says that the impedance of these pins is like 25 ohms. Cool. So that means that so a differential pair, the impedances add up. So that means that each line should be 45 ohms of impedance. So assuming that we have a near zero inductance and capacitance, we assume this and then we just make it work later. Okay, assuming that, then we should have a 45 ohm-ish resistance on each of the lines. So I've got 25 ohms here, so I add a 22 ohm, which is a common value, and I call it a day. Close enough to 90. I probably lost some people along the way. This is fine, okay? This is absolutely fine. Like we are going to implement this schematic exactly once, and then you're going to do what I've done for the rest of my life, which is just take it from the same file and just copy it over to every other board I've ever done. Okay, so I explained it here again, but the ESP32 output pins has some resistance. We add to that resistance to reach about 90 ohms, and that's like, it's impedance matched enough, it's fine, okay? Yeah? Yeah, so everything has some impedance, right? But the thing is that like we just get close enough to 90 ohms, and like this is a USB 2.0 or something, it's not very fast, we'll get away with it. Yeah.
Impedance matching only matters for high frequencies.
Like USB or like really, really fast SPI or whatever.
You can get away with it if you don't put like those resistors. You can get away with it.
Yeah, it's not the worst thing in the world, okay? We're just doing it to be slightly better, but we're not gonna be too fast about it, okay? So, okay, moving on. If you didn't understand, it will not affect your life at all, okay? That was a TLDR. Put 22 ohms between the D- and D+ and the GG and the IO pins of the ESP. Has everyone placed their resistors? Is it 22 ohm or somewhere around there? 22 ohm is a common value, you should use that. Why are you looking at me so disapprovingly? Okay, moving on.
It isn't necessary if you do the impedance matching correctly.
Huh?
Those aren't necessary if you need impedance matching correctly. Those are more like a production bodge.
So I've been production bodging all my own boards.
Yeah, but USB lines should be short enough that doesn't really matter, but still.
I mean, yeah lah, my USB lines are very short, so it's fine.
You shouldn't the impedance calculator yet.
No, that is in future lessons.
Okay.
Okay.
Move that forward.
Huh?
You might want to move that bit forward.
I will not, because we're not gonna do any other impedance matching.
Okay.
Yeah. Okay, this is good enough. Alright, so now we have enough to like make the board work. I'm going to delete my application. Oh wait, no, we do not. We still need this. Okay, I made a note here. The bottom two pins of the ESP32, IO47 and 48, they are not 3.3 volts like the other pins. They are 1.8 because they wanted to be special. Therefore, we cannot use them for most things. So just put a no connect flag on 47 and 48 as well. Hover over it and press Q, like this. Huh?
Wait, not their 1.8 volts.
Some stupid low logic level, annoying. Most circuits are either 3.3 or 5 volts, you know. 1.8, like you can find plenty of components which are 1.8 volts. Stop looking at me like that. There are plenty of circuits which are 1.8 volts, but like usually for hobbyists we don't like really bother, you know. All your breakout boards are gonna be 3.3 volts anyway, or 5 volts.
This is for like serious stuff lah, basically.
Yeah, 1.8 volts is for like weird stuff which like you are unlikely to use.
No level.
Not yeah, it's a lower voltage level, like uses less power and like whatever. It's like nobody cares. Okay, all right. Okay, we need two resistors here. So 45 and 46 need to be connected to ground through 10k resistors. So again, place R.
All this is in the data sheet, yeah.
Yeah, it's all in the data sheet. Like you can go and read the data sheet if you wish, but like I wish I didn't. Okay, so 45 and 46 need to be connected to ground, like that. They need to be connected through 10 kilo ohm resistors.
Why? Just don't really shoot. No reason why.
It's just like that, bro. Don't worry about it.
What do we do when people
Oh my
forgetting
God.
how inductors work? What do we do when people forgetting how inductors work?
You determine whether forgetting how inductors work affects your life, and if it doesn't affect your life, then you just forget. Yeah.
Makes sense.
Okay, I think that's actually everything. Do I need anything else? Oh yeah, boot and USB enable are probably important.
10 kilo ohms, right? Both?
Yeah, 10 kilo ohms. Bro, I keep forgetting resistors. This is terrible. Boot needs to be high.
Pull up to high, yeah.
Yeah, boot needs to be pulled up to high.
Have you explained clock resistance?
Oh, this
We haven't. You want to explain?
Okay, so the reason why we add a resistor is those are normally pull-up resistors. So you just want the value of that pin to be 3.3 volts or ground, depending on what the resistor is connected to.
What?
Yeah.
How does this clock resistor make any difference to the normal resistor?
It's-
We call it pull-up resistor. It's just a resistor.
Because it pulls up to the voltage rail.
Yeah.
The opposite of it is called a pull-down resistor, which pulls it down towards ground.
Yeah.
Okay, basically, this pin, IO0, this is supposed to be at 3.3 volts. If we simply short it to 3.3 volts, then like there'll be a bunch of power going through that line, correct? So you can think of it as a current limiting resistor in this case.
Plus, when the microcontroller starts up, it's looking for like some configuration pins. If they aren't in like a known position, they will just go haywire and then like the application won't reliably work. So you want to ensure there's reliable inputs on those pins when it starts up, and then later on,
Yeah.
because it's a pull-up resistor, you can just use it as normal GPIO afterwards.
Yeah.
Albeit with like slightly different properties.
Yeah, so for that pin IO0, that's the boot pin, and you do not want to leave it floating, which is not connected. You do not want to leave that pin not connected. Yeah.
one tangent is good.
Okay, I get it.
If it's not connected, you act as an antenna. You can pick up any stray voltages from the air and like basically not good. Yeah.
Did
So-
that not make sense to anyone? It is okay. It is okay if it did not. We will attempt to explain again.
Yeah.
Slightly not make sense, but makes sense also.
yeah, IO0 connects to 3.3 volts with a pull-up resistor, which means that it's a 10k resistor connected to 3.3 volts. Then IO3, 45 and 46, they are pulled down, which means that we connect it to ground through a resistor. Okay. Okay, even if like nobody understood, we'll try and explain again later with like a clearer example. For now, just do this, it's okay. Yeah. What?
No, that's normal. 10k is normal.
There's a very wide range of resistor. The standard range is 50 or
So like
10
100.
power 0 to 10 power 6 or so. Or 10 power 7.
7, yeah.
Right, that's the standard range.
so from 1 ohm to like 1 megaohm. That's the normal range. Right?
10 power 7 is about 10 megawatt.
Yeah.
That's like the normal-ish range.
What's the point of the resistor, or is that just basically?
Okay, I'll attempt to explain again. Okay, look at all of these pins. Right now, they're not connected to anything. So what voltage are they at?
No.
The answer is nobody knows.
It can be
Yeah.
anything.
Yeah.
It could be anything.
So when something is not connected, we call it NC, or which NC stands for not connected, or we call it floating. Okay, so when something is floating, we don't know what voltage it's at. It could be anything. Like this ESP32, this is like a magic box, you know, and we may not know exactly how it behaves inside. So we don't know what voltage is at all these pins which are not connected. So I'm gonna disconnect this for now. IO0 and IO3, these are configuration pins, which means that when the ESP32 boots up, it looks at these pins and sees what the voltage on these pins are. And it will behave in a certain way depending on what voltage these configuration pins are at. That's why we call them configuration pins. We set a voltage to these configuration pins to configure the ESP32 on startup. Okay, so that's what that is for. Now, if I leave these floating, I cannot guarantee that when my ESP32 turns on, that this is at the voltage that I wanted it to be. So what I do is I connect them to power or to ground or some other configuration voltage, and this guarantees that my configuration pin is at a known state upon startup. It's not floating. We know what the voltage is, and therefore it has a defined behavior.
How does the resistor count by define logistic? Or is logistic just one power?
So the way it does it, like you could just short it to a power wheel. It doesn't really matter, but for
Safety purposes, just for resistance?
yeah,
Okay.
basically for safety purposes, it was yeah.
Because imagine that this thing like will dead short to ground inside somewhere.
Yeah.
Then you don't want to connect it to 3.3 volts directly.
Because that is an input pin. The boot pin is an input pin usually. Input pins have high impedance, which means depending on whether it's configured as input or output lah. But like, so that's why we put a pull-up resistor. So the value of the resistor doesn't really matter in this case.
It's just like to prevent it from instantly sending like 3.3 volts through it and potentially breaking.
Yeah, you can think of it as a current limiting resistor.
Yeah, so for example, if that pin becomes an output pin, it tries to pull the pin to 0 volts. Then now you have a dead shot to ground through the microcontroller and notify it. Yeah. Essentially that's the reason why you have a pull-up resistor, not or why you have a pull-up resistor then not just connected to 2.2 volts.
Okay, this will probably be explained 2 or 3 more times during the course, so do not worry, because we use pull-ups and pull-downs all over the place. Okay, but for now, does everyone's application schematic look similar to what mine does?
Do we need anything else?
For now, we don't need anything else. I'm gonna go around and check everyone's work.
you have a wire, the voltage and like then it doesn't sound up there. That's why. So that's why the high impedance happens. Because like resistance is down. Yeah. So essentially, because the input pin has high impedance, probably in the order of 1 ohm, but like because of that, it doesn't really matter. If you use 100K, it's probably okay. Like 10K is usually a good value because that is in the order of microamps in like say using 2.5.
It's just because like the resistance value is small enough that it doesn't affect the
If you want high impedance, the way you can think of it is when you're measuring a thing, like you will consume like maybe 1 amp. So why does it consume 1 amp? Like 2.2 measuring 2.2 will consume 1 amp. So if it consumes more current, then the resistor will become so let's say it consumes like 1 amp. Then the resistor will have the potential to get current. And now that thing is no longer 2.2. But you want it to become roughly because that's logic level. So that's like the more that's like, but that's the actual reason, right?
So when there's like a low voltage, that's not flat. You can
Yeah.
stabilize it.
Yes, so because when it's not connected, it acts as like antenna. So if you pick up straight status, and if you just when you measure the feed, it will be 0 or 1, as you know.
I wonder if I
So that's why it's not
think about
flipping.
any compensation of
So that's why you need.
the spacing between here if I want to
Yeah,
lower
yeah.
more.
Actually,
It doesn't matter.
I should have put the clock resistors.
Yeah.
It's like make it cast. It's complementary to each other.
Correct.
If you want to
Radio
play,
signals, because
Like, I mean, this actually is sketch, right? For the basic form. If I want to make this actually a sketch for so find
Yeah.
out the two pieces that's like exactly complementary to each other.
Yeah. If anything, we want negative tolerance.
Because the reason will be formed. Oh, curve.
the higher the impedance and the more willingness of the set.
Like say resonance or the bit of before the curve.
Oh,
But the laser curve is not uniform. It's usually like a sort of flat
yeah.
Yeah, I've whacked like that before. Yeah.
That's not good. Because you can configure it in software. You can configure in software to be a
Like it's different that much matter.
But yes, instead of it's configurable in software.
Is that the entire like default
This is my full application schematic. It's not like super important.
okay, but actually you have a lot of what you call it.
Net labels.
Yeah, but like where do they connect?
In this case, I haven't connected them to anything. Yeah. Okay, guys. Guys. Okay, so we are done for schematics for today, pretty much. Okay, no, we'll come back to it. But for now, I want to like quickly jump to layouting. Okay. All right. So press Ctrl S to like just to save your work, and then go to Assign Footprints. Assign Footprints, and then you should see a menu like this. Okay, and I've deleted everything extra, so now you should see exactly the same thing that I'm seeing. Okay, maybe your like component designator numbers will be different. So maybe like these numbers will be different, but generally you should have the same stuff that I have. Okay, can I zoom in? Of course not. Suffer, I guess. Can I zoom in? No. Okay.
Do you have a magnifier to...
Or you can set your Windows default scaling.
I'm not doing that. I'm trying to like make sure I can annotate, but I want to zoom in, you know.
Oh.
Wow, technology!
How do we access that?
Oh great, now I have to zoom back out, yeah. Okay, the way you access this is I'm in the schematic, I go up here, assign footprints. Fourth from the right. Okay, so to reiterate one more time, footprint is the physical shape of your imaginary component. Right now, these are just ideal components floating in some imaginary space. We need to actually like assign like a body to them, you know, not just the idea of them. So that's what assigning footprints is for. All right.
Anyone have like a region laptop because it's dying?
Okay, so all of your capacitors and resistors, just put 0603 for now. Okay, then your USB B micro, we settled that earlier already. And your ESP32S3, the footprint should be called ESP32S3, okay? Okay. Let me zoom in again.
Behind here.
Oh, thanks.
Does anyone need help?
Sorry, someone else.
Yes.
Why is this something cat does not look? Comical. Like you like that's funny, but if you don't use
Oh yeah, so basically what that already affected.
So what this is, this is the internal schematic of the audio. Basically, ESP32 comes in chips. But then,
Okay, the footprint
This is an ESP32
also
yeah, but it's like a huge
so inside this
are like
By the time it came with the monitor,
this is the
the
chip,
drive,
which is tiny little black line.
but
But all of the components are in okay, and all of this is happening inside chips.
So the best
Basically, your system on chip is
this is
that's
a
why
great
it takes time to
so
go
fast compared to the
technically it's okay.
maybe it's okay, but like
Yes, that's actually like stuff inside, you know. Yes.
heavy components.
I actually like, I don't mind like the weight because I do.
Okay, has everyone assigned the footprints already? Is everyone okay? If you got footprints wrong, you find out later. It's not the worst thing in the world. Where did like half the class go?
Oh, okay, this one has the physical
Oh no.
Oh, okay. This one, it gets scratched very badly from the outside. Yeah, this one is just so dumb, you know. I walked into a wall. Okay, that is a wall. Like not a wall, but like a door. You know the door handle. Yeah, I walked into the door handle.
I want to continue. Guys, I'm continuing.
Okay.
There's too many components, too much
Okay, so now that we've assigned all of our footprints, let's go to the PCB editor. So the PCB editor is the big green button, okay? So again, you'll see this like dark mode window, alright? Go to tools and go to update PCB from schematic.
If I already have a schematic and I update it, you just bring it up to date, right? It will not.
It will not delete stuff that's already there.
Oh, okay.
So if you are not sure, you have to then just delete everything and like try again.
Okay.
Yeah. Okay, so update PCB from schematic and close and place. Alright? So place, like you just left click and you'll like place it down wherever. Alright, and you'll place it in some kind of arrangement. Doesn't matter. This is not a suggested arrangement. This is just an arrangement. We need to arrange it ourselves. Alright? Okay. I'm gonna put this here. Alright. Let's take a look at the side for a bit, alright? So check it out. I've got all these layers. Okay? So layers, they represent different things, alright? So by default we have a 2-layer board, which means that we have the front and the back of the board, or more specifically the top and the bottom. Okay, so like we can place things on either side. Okay? So if I just look at my board right now, it just looks like that, right?
Where's the button again to see?
It's the 6th from the right. 3D viewer.
Oh, okay.
Okay, so right now all of my parts are just at the top. Okay, this is my USB port, which I don't have a 3D model for, but that's fine. Okay, by default all your resistors and capacitors, they're common, they're normal, so like they will have a normal, like the 3D model will be there for you already. Okay, now I can click a footprint and I can press F. Notice how it turns blue and like mirrors. Click it and press F. F is for flip, okay? So what flipping does is put it on the other side of the board. So if I look at the 3D viewer again, look at that, it's on the other side now. Okay? Now this is very important for when you want to fit everything in a small space. Okay? We're not going to touch it much for the purposes of this course because we don't care about saving space. But if you're doing an application that's very small, yeah, it matters, you know. Okay, so can press F to flip it back. Alright? Okay, now, take note. This is a 2-layer board by default. Okay? So, you should see F.Cu and B.Cu. Cu stands for copper. It's like the element of copper. Okay? So, does anyone see other Cus besides F and B? Right at the top. You should only see 2. If you see more than 2, then like you have like a 4-layer board or something, and like I'm not sure what's up with that. Okay? Okay, so basically what this says, a PCB is like a plastic square. More specifically, it's made of like a green fiberglass. Okay? And we can place copper on the top and on the bottom, which means we have 2 layers of copper. And those layers can have wires on them and they can have components on them. Okay? So hence we have 2 copper layers, F and B, front and back. Okay? Now, in a 4 or 6-layer board, which we're not going to touch for now, we'll talk about it in like lesson 7, okay? But basically, I can have more layers, which means that I can have more wires running around. If I have everything only in 1 layer, then wires can never cross over each other. They can never intersect, right? So, only with multiple layers can I do a cross. And there are a lot of things which you can only wire up by crossing wires over. So if you have a lot of components, you just add more layers, and now you can cross over in more ways. You have a lot more flexibility with routing. Okay? So, for the purposes of layout, we call a wire a trace. Okay? So, we place a wire by going to this button here, Route Single Track. It's the 4th from the top, next to the layer count.
These are real wires, no longer ideal.
Yes, these are real wires now. Okay? Now, I can place a track and look at my rat's nest. So my rat's nest says what should connect to what. I'm just gonna connect something like ground, okay? Check it out. I clicked a ground pad, and now that I'm trying to put a trace, it highlights everything that is belonging to the same net. Okay? Is anyone confused? Have I gone too fast? Yes, no problem. Okay? Okay, so do we accept what a trace is? A trace is a wire. Okay? Now we remember what nets are. It's a set of points that need to wire to each other, right? Okay, so I can click the trace button, and I can try to wire two things together. This is a ground pin. See, it's labeled ground. So I can click this and just move my cursor out, and it will like try to drag wires to it. Okay, now check it out. Look at this. See this? All of these have been highlighted because they're all part of the same net. Ekicad is telling me, hey, all of these are potential places your trace might want to go. So you don't need to like manually go and find. If you stare at it, yeah, that's highlighted. Just connect to that, you know. It's more complicated than that for like impedance reasons, but like for just the purposes of wiring things together, yeah, just connect all the highlighted stuff together. Okay, so
you can just not care about impedance. Yeah, like if you just want to make things work.
yeah, just don't be high speed. It's fine. It's fine. Okay, so for example, I can take this and I can wire it to this. I can just click the other side, and the moment I click, I've placed the other side of the wire, so there's nothing left to do. It will exit automatically. Okay, I can demonstrate that again. Here's ground. And now look how this trace is highlighted. This entire trace is part of the ground net now. I don't need to wire to a pad. I can wire to the trace. Okay? There's nothing wrong with this. This is fine. Is anyone stuck? Anyone cannot find the trace button? Stop laughing at the USB port. You are in the guys. Everything that you need to be in a certain layer, okay? So like I need F, or depending on whether you're an F or B copper layer, it will default to trying to place traces on front or back. So in this case, I was mistakenly on the back layer, and everything is red because it's on the front, right? But the thing is, when I connect to a red pad, it automatically knows he's wiring to a front pad. Cannot be that he's on the back layer. So it switches. So during the trace routing, it puts me in the front for me. But the moment I leave, the moment I'm done, then it switches me back to back. See? Because that's where I was. So if you start a wire from like nowhere, then it will be on the layer that you were on. If you started from like a pad that is on this layer, then of course the wire will be on that layer also, right? That makes sense, right? So if you try and route something and you're on like the back layer, then like look, my wire is blue because it's on the back, right? Red is for front, blue is for back, right? Okay, so if you're having like if you're running while your trace is blue, this is why. Okay, yeah. And I can just have a trace here and then check it out. I'm gonna go back to my 3D viewer. See my traces? This is on the front, right? Wow, traces. And I look at the back and I just got this one trace here. This is the back. This is the back side. Yeah. Okay. So this is what we're really doing. So make sure you're on the right layer, basically.
Okay, and I just need them all to be like connected, but I
Don't go too far ahead. Don't. I'm just demonstrating how wiring works. Okay. I'm going to wire things properly later. Okay, guys. Is anyone confused before I move on? Yeah, I'll show you later. Okay, I'm moving on. I'm going to unroute everything. So, what you can do is I'm gonna click the ESP32 and like right click and go to unroute, and it's gonna delete all the traces connected to it. All right, this is a shortcut. Okay. For now we only care about FCU and BCU. Okay. All the other layers do some magic, and we don't care what it is for now. Fair enough. All right. So let's stay in FCU. Alright, let's take a look at our rat's nest, okay? So our rat's nest says what is supposed to be connected to what. So as I move my parts around, the rat nest moves as well. Alright? The rat nest is not a wire. It's just telling me, hey, you haven't wired some stuff yet. Okay? So, usually when I'm routing stuff, and I'm not really an expert on like how to route things properly, but like usually what I do is I try and make the rat nest look as bad as look as like not bad as possible. So for example, look at this. This pad is connected to this pad, and I know that because there's a rat nest line here which is connecting them. See? So I just want to wire this pad to this pad at some point. I'm gonna rotate the resistor so that the ground faces away from the other pins. And this is just so that later when I route other traces away like this, like the resistor is not gonna get in my way. Okay. Then I can just route this to this like that and connect it. The redness disappears. It disappears because like, hey, he wired it already. I can go now. I've done my job. Is anyone confused? Brother is like playing with the wood instead of listening. It's fine. I'm just joking. Okay. So see this trace? If I want to select the trace, I have to press U and it will select the whole trace. Because there's like this straight section and this straight section. Okay? So whenever I have a trace from somewhere to somewhere, like here to here, you know, if I click a trace, it will only select that one straight line section of the trace. If I delete it, it will only delete that section. If you want to delete the entire trace, you have to like press U. And then that will select the entire connected trace. Alright? Just a side note. Okay, is everyone able to... Is everyone understanding what I'm saying so far? Is everyone alright? Yeah, any questions? Okay, I'm gonna assume there's no questions. Let's just take a second to go into the layers. There's F fab and B fab over here. Let's just hide them, okay? So F fab and B fab, these are fabrication layers. Basically, they're labels for the fabrication company to look at. For us, they're just getting in our way and making the thing look confusing. Let's just hide them first. So now you can see all that's left is the footprints and the reference designators. Okay? Alright, let's continue. So, what's C1 for? Actually, C1 is a decoupling capacitor, right?
This is what I'm saying.
What thing? Oh yeah, shouldn't.
So if you click one here, it'll highlight it there.
Okay, so we split screen and we put the footprints, the layout editor on one side and the schematic editor on the other side. If you click a component in layout, it will highlight it in schematic.
You can also get pads. So for example, if you want to get like the 3v3 net, you just like click this segment, press the wavy thingy next to the one.
Tilde, yeah.
Tilde, and then it'll show you everything that's...
Okay, to repeat that a bit louder, tilde will highlight a net. Okay, so tilde is the little wavy button. I don't even know how to describe it. It's the approximation sign, okay?
It's above your tab.
It's above your tab key, yeah. So you can hover over a pad. This is a 3.3 volt net pad, right? I can tilde it, and now it will highlight all of the pads which are supposed to be connected to it. And not only that, in your schematic, it will also highlight the net blue. Is anyone lost? I think it's normal to be lost.
Fine. Very good. Alright.
Also, if it gets complicated enough, it gets really trippy. Because if your circuit gets complicated enough, it gets really trippy.
Yeah, I can see now. I can see why. But right now it's okay. Also the other way around.
True.
Yeah, you can like select like something and then like
Like if you're doing it markdown, that symbol is
Okay guys, I'm moving on again, okay? We got a bunch of stuff to do. Alright, so you can press these two buttons on top to rotate back and forth. Okay, this is gonna be different from between mine and yours, okay? My default rotation angle is set to 15 degrees. Yours should be 90. Okay, so I'm just rotating my USB port like this because I'm pretty sure, yeah. So here's the USB port is gonna be connected. D minus and D plus is gonna be connected to like these two pins here later. So I'm just gonna arrange it somewhere near there first. What we're doing now is we're trying to untangle the rat's nest, okay? So we're trying to like stare at the thing and go, okay, how can I arrange this such that the wiring doesn't look terrible? So look at this resistor is connected between this pin and 3.3 volts. So this connects to this, and this connects to 3.3 volts. You can move closer if you can't see, by the way. But like, I rotate this, and now this net is right next to this. This is right next to this. See? So I can just wire these two together later. So what we're doing now is rotating and arranging components in a way that makes sense, so that all the wires are short and straight and generally clean, and we don't have to do too much like funny routing. We can already start routing stuff together if we want to, like this. Just start wiring it together. Okay? Where does R6 go? It goes here. So I can rotate it like this. Okay, take note. Notice how all of our footprints have this, what is that, purple?
Oh yeah, the courtyard.
Yeah, so they have this boundary around them. This is called the courtyard, okay? So the courtyard of a footprint basically says you are in my yard, nobody else is allowed to come in my yard, okay? So the courtyard defines how close you are able to place things before they start overlapping. So look at that. The other resistor is like flashing red. It's too close together now. So if the courtyard intersects too much, then it's not possible to assemble in real life. Did I lose anyone on that? Is everyone okay? Alright, great. R35. Who is R35? Oh, it's you. R35 and C22. These go to the enable pin. These go to the enable pin. Okay, so we just continue accordingly. So yes, my laptop is taking off. Fly. Alright, so here's my RC delay components, okay? R35 and C22. You're probably gonna have different names for it. I'm just gonna move the numbers out of the way so that they stop annoying me. Now take note, I didn't just place this directly here. That would make it very convenient to route this to this and this to this. But now my 3.3 volts has to like do this, you know? So that means that I cannot have a fatter trace for the 3.3 volts. Now, the width of a trace determines its current carrying capacity, okay? And also its resistance, and hence its impedance, okay? So for power tracers, it's nice to use a fatter trace, alright? So you can go to edit predefined sizes. So track, use net class width. Net class width is the default width, which is usually 0.2 mm. It would be screaming if I did that, yeah. Okay, net class width, and then go to edit predefined sizes. So you should see this. Does everyone see this? I'll wait, okay? Is everyone okay? I'll show you again. It's fine, it's fine. I'm gonna full screen this. Alright? So go to this box down here. Use net class width. So this basically says what our track width is by default. By default is 0.2 mm. Okay? So I can click that, and I can go to the drop down. I can go to edit predefined sizes. I can click that, I can add a width here in the little plus button at the bottom. Alright? So I'm gonna add 0.5 mm because I like that number. Okay, that's probably gonna be good to like 2 amps depending on stuff. It's fine, it's fine. Alright, okay, so then I press OK. So now, when I go to my drop down, I have net class width and I have 0.5 mm. So I can select 0.5 mm. Does everyone see this? Like, do you have that on your own screen? Because being able to do your own track width is quite important. Okay. Alright, so I'm gonna demonstrate. I've set my track width to 0.5 mm, and now I have nice fat tracks. See? These are way fatter than the tracks which I had otherwise. So here's my 0.2 mm track, and here's a 0.5 mm track. So this is going to have much higher current carrying capacity and generally lower resistance and impedance. Okay? if I'm not wrong, fatter tracers are also less prone to EMI. Okay, forget about that. I'm not sure. More prone, is it? So? Not sure. Okay, never mind. Forget about that. Forget about that. Nobody cares about EMI anyway. So for our 3.3 volts and ground, we'll route it using fatter tracers so that it has more current carrying capacity. But for regular stuff, we'll just use a net class width. Okay, so like this. So I gave myself decent space so that I can route this out nicely later. Yeah, okay, that's better. Is it better? Yeah, but then my 3.3 volts has to cross over my ground.
What do you mean? It just goes straight there.
And then
wait.
crosses over my... And then when I route my ground, then I have to cross over, then I need to use a VR.
That might be stupid.
3,
That is sad.
15. Okay, yes, everything is fine, everything is fine. So just route accordingly. By the way, guys, it's okay if your thing doesn't look exactly the same as mine, okay? This is a whatever. I'm showing you an example of how to route things together, but the key idea is that you learn the skill and then own self go and arrange, okay? It's fine if it doesn't look exactly the same. Is anyone confused about what I've been doing so far? Yeah, I changed the thickness of the wire so that it's got more current carrying capacity. Okay, your 3.3 volt net is going to go nowhere, okay? Like, right now, there's 3.3 volts is coming from some magic place. We don't know where it's coming from. Next lesson, we'll show you how to actually make 3.3 volts on the board using, like, regulators and power supplies, okay? But today, we're just wiring stuff and, like, just showing you the ropes, okay?
It's going all over the place, but yeah. Wait, but actually, I still don't understand how do we make a calculator on this? Something simple.
What does the calculator mean? Screens at the bottom. Screens at the bottom, right? Okay, so next, I think after lesson, we can show you how to add buttons to things if we have time. But I think we'll have to spill over to the next lesson. But basically, right, you're implementing the microcontroller now. Everything else is just a peripheral, just connected over. So you can add buttons to this thing, you can add like a screen to this thing later. So you can make a calculator out of that.
So right now what we're doing is we're just powering the ESP.
No, we're not even powering it. We're just adding some critical infrastructure to it that makes it work. But like we haven't added power to it yet actually. We've added the decoupling capacitors in preparation for adding power, but the actual like power is coming from nowhere right now. You know? So like the next lesson we'll talk about how to get power onto the board.
Yeah,
for now there's no power.
Oh wait, actually I do have something I want to do. This is for my idea, but we want to make this something like LED related something.
Yeah, that's absolutely fine. We can do that.
Okay, good. Because yeah, like right now I'm like I know what we're doing, but I don't see what we're doing.
It's fine. I mean, yes. This is all preparation, and more importantly, showing you the skills. Okay.
So next week we'll be like doing something like more tangible, I guess.
Yes, like we'll be powering this. The ESP32 S3 is a really great general purpose microcontroller. You can do math, you can do whatever on this. You just run software on this thing. Right? And if you can run software, you can do anything, right?
Yeah, I really want to do.
And then you can use the software to control things, right? And the things can be literally anything, right? So like by starting with this, we open you up to be able to do basically anything. That's the idea. And like next lesson we'll teach you how to power the thing.
Next year.
But when you this is conquer this loop is now a loop and a loop. Yeah, this is unentangling. That's what we're doing.
Yeah.
Interesting.
I haven't thought it yet. I don't intend to teach it yet because like my is going to like 8 components of the course, like shouldn't be any problem.
Wait, there's a trick to doing this.
Doing what?
So that's why you
Aligning the traces. I'm assuming there's like a mathematical way to optimize this.
Okay, 那其实好说。
Because right now the wires can't be
you can't do that.
But this one like okay, like for example, this one, right? If I want to connect this to
Guys,
to go the
I want to show you something.
like this is to go the long way.
Guys, so he's having problems routing. He's having problems arranging his stuff, and the reason why is because his grid is set to like some huge number. Okay, so grid basically locks you into certain arrangements. So for example, if you have a 2.54 mm grid, then it means that I can only move things in multiples of 2.54 mm. This is very so it will like snap to positions. Okay, this is useful for arranging things. So you can, for example, if I have 10 resistors, I can like snap them to like a specific spacing from each other. The problem is when you just want to arrange stuff and you don't really care about the exact position, just the like shape of it, then it can be very annoying to have the grid be set to some number because like, look, I want to move this close and like I cannot move it close enough because it's gonna like snap into the board, right? So what we do is we just set the grid all the way down, 0.01 mm, and now you can do basically whatever. So go to here and select the grid, the smallest grid size.
It works? I guess.
Then you can move things around much smoother.
Also, how do I like bind it to the spot so that we move together with?
Well, once you've routed something, you can't.
Oh, I shouldn't be moving it.
Yeah.
Okay.
Guys, another side note, right? Let's say you've already routed something and now you want to move it. When you move it, it just creates 2 more rat's nests. The tracers will not follow. Okay? So if you ever want to move something, you need to reroute the tracers. Okay? So either just reconnect them, or ideally just remove the trace entirely and just route from scratch again. Okay? Something like that. Alright? So you can't move stuff once you routed it basically. The tracers will not follow. It's not like a schematic. Okay? Schematic, when you shift stuff around, the wire will just drag along with it, right? That's not like that in layout.
Yeah, but I think I'm hoping that I don't need to. I know the majority of the most famous courses.
I did not, Marcus, did not explain the decoupling capacitors, please.
I did last lesson.
No, but like, in practice.
Okay. Okay, guys. Remember how last lesson we talked about decoupling capacitors? It's time to do that for real, okay? So we've got C1 and C2, and these need to be placed as close to the power and ground of the ESP32 as possible. Alright? So let's get rid of the RC delay pin because I don't care about this for now. Wait. Yeah, unroute. Oh my god. Okay. Oops. Okay, let's just get this out of the way. I'm gonna move C1 and C2 as close as possible to my ESP32. Alright? C1 and C2. Alright. C2 is the smaller one. It should go nearer to the ESP32. I'm just gonna rotate it like this. Okay. So, we need the lowest impedance possible connection between this and this. So, you can use a trace just like that. Oops, my bad, sorry. Just like that, this is fine. Okay. And then same for ground. Alright. Then your C1 might be a bit further away. Just because of constraints. Usually like this will be nearer to the power supply, which we haven't placed yet. So we'll just place it here and this is fine. It's still useful to have multiple capacitors on decoupling the same voltage rail because for different frequency noise on the voltage rail, different capacitances are more or less effective. And nobody cares why. Yeah, so just wire your decoupling capacitors as close as possible to your 3.3 volt and ground input pins on your ESP32. Okay? And this ensures the lowest impedance path and ensures that the decoupling capacitor has the fastest response possible. Did I lose anyone? Is everyone alright? Why not, right?
Let's say you're soldering and a stray ball of solder flies onto the shorts.
Skill issue.
But like, try your best.
I mean that's accurate enough, right? Guys, remember to press Ctrl S now every now and then.
Yeah. Sometimes if you design too well, it can crash. It has crashed on me like at least 10 times before in the past 3 months.
Yeah, it's crashed on me as well.
Always say the word.
Okay, we're gonna route the USB. I need a little bit of attention on this. Okay, so the USB port, like I said, is a differential line. Alright, so we need to actually route it not as a regular trace but as a differential pair. I'll show you how. Okay, this is something that you're most likely gonna be doing very rarely, so it's not the worst thing in the world. But for the sake of doing things correctly, we'll just talk about it. Okay. So look at the rat's nest. Okay, I'm trying to align the resistors as symmetrical to this as possible. So the tracers connect from the port to the resistor, through the resistor, then connects to the ESP over here. So I'm just trying to make this kind of as flat and straight as possible. Okay. Now, if how do I switch to differential mode? Is it
6.
6? Okay. So I press 6. I didn't know that shortcut, by the way. I press 6 and then I click the USB data line. Now, KiCad knows that this is a USB port and that it has to be routed with a differential pair. So it will not allow me to route VBus with a differential pair. See? Unable to find differential pair net.
Oh yeah, for this you have to set the name, you set the net label, net link properly. It has to have either a plus and minus or a P and N inside at the last character.
Yeah. Okay, so I put the differential trace here, and if I actually try and connect it all the way, I'll just freak out. So we connect it most of the way like this. Alright. And then go back to regular traces and connect it. Yeah. I need to try and make it not, yeah, like this. Okay, so basically you want to keep the parallel spacing for as long as possible. Alright. And you want it, and in general you want the differential trace to be not be excessively long. So in this case mine is really short. Okay, this is pretty good.
So you keep it parallel so it doesn't get interfered with. So
Yes, that's right.
That's why you have to pair.
Yeah, good enough. Okay, this is not like amazing, but it's good enough for like whatever we're doing. All right, I've done way worse on USB line. It's fine. So then just take this and again 6. Does this work? Ooh. It's supposed to be, but
No, it's not. You didn't label the inner one.
yeah, I didn't. Whatever. It's so short, I'll just route it normally. Yeah, good enough. Okay, so why does Dylan look horrified? Okay, great. So you need to route it as a differential pair basically, alright? And if you make this really long, then stuff will start breaking because it absorbs too much interference from like the universe. So don't make your USB longer than it needs to be, you know? If I unhide the fabrication layer, you see that here's the PCB edge. Okay, so you place this as you place it such that it's right at the edge, and then like you route all the way in. So if your board is like gigantic, then this need to be further away, right? Then your line will just be longer, no choice. Okay. But for me, I don't care how big my board is, so I'm just gonna like place it like decently close, and it's fine. Does everyone understand what we're doing? Why does this look so terrible anyway? Why does this look so terrible anyway? I'm gonna try and like make this less.
I think I just
Yeah. Okay, that's better. Okay, does anyone have any questions?
So the mystery chip is also solar.
Generally for routing these lines, avoid sudden sharp bends. So 45-degree bend is fine, but you don't want like too many others to happen in quick succession, you know. That right there, that's like funny discontinuity. Yeah, that's one good. Yeah. That would have been yeah, nice. Yeah. Okay, so generally USB lines you want to be as short as possible and as differential as possible. You know? Yeah. I've done USB lines where like it wasn't a differential pair at all. That's all it is. That's because it was like super different. Guys, I know a lot of you are having problems connecting all of your 3.3 volt and all of your ground together. I'll show you like an easy way to do that in a second, okay? But for now, I want to define the size of the PCB. Okay, so we've routed most of our stuff. I haven't routed ground at all, and I barely routed power. Okay, we can't really route power anyway because we don't have a power supply yet. But we could have routed all our ground, right? But before we do that, let's go to edge cuts layer. Edge cuts. Is everyone able to find edge cuts layer? Edge, like edge of a table. Yeah. Is everyone able to find it? Okay, great. So I'm gonna draw a rectangle, okay? So I'm just gonna draw some rectangle of like some unknown size, whatever. And then I'm gonna go to 3D viewer. So this is the size of my PCB. This is what edge cuts defines. Edge cut defines the size of my PCB, okay? So I drew a rectangle just now with the rectangle tool over here. You can do this for silk, you can do this for like anything, but usually we use it for edge cuts or for silk screen. Silk screen is the labeling on the board, okay? So look at all these numbers. This is the silk screen, alright? So it's this yellow numbers that have been following us the whole time, which we can drag around and do whatever to, alright? So of course you have front and back silk screen. In this case everything's on the front because all our components are on the front. Anyway, rectangle is usually used there or in edge cuts. So I'm just gonna make this the size of the board. For now, unhide your F fabrication layer. So because the micro B has to stick out the PCB edge. So unhide your fabrication layer. Is everyone able to find the fabrication layer? Okay, great. So just pull the PCB edge until that point, okay? It can be like slightly in, but like don't try to be accurate. Yeah.
And wait, do we let the antenna stick out?
The antenna has to stick out.
Oh, okay.
Okay. Need is a strong word, but like generally yes, it should stick out. Okay. Auntie, you good?
Where's the rectangle?
Oh, it's here.
Oh, by the way, is this different from like the source channel they give us like the white thing with like the things you just take the wire stick thing and the thing. Is this different?
That's a breadboard.
Ah.
That's not a PCB.
Ah.
That's like literally a big row of sockets, and then like you can put things into the socket, and some of the sockets are wired together.
So it's like.
So it lets you connect things. It's not this. It's not this at all. No, it's not the same thing. You know our breadboard is a bunch of nets. It's a bunch of nets that you can plug things into. Okay. So whenever you plug things into the same row, then you have to shorten them all together. This is how you wire things to a breadboard. This is totally different. We're actually designing the whole circuit ourselves. On a breadboard, it's just a bunch of nets, and you have to wire things up to it. Right? Here, all our wiring is being done with the tracers. See all these tracers?
How much does it cost to print just this product? Like what we have right now?
Like without soldering?
Oh yeah, we're just
You're gonna like sew into a case or something, and then you're gonna set. Is anyone stuck? Is everyone okay? Okay, no.
I thought it's last week, right? 5 ago? Actually, what's the button? What's the possibilities?
Drag it to the PCB edge. That's the
I can see yourself. Yeah, you don't need to connect now. What's the properties that you have other than that?
Okay, guys. So this edge of the PCB where the micro B connector is, that's basically fixed in place, okay? Like, we can't really move that because then we'll violate the design rules for the USB. And for this side of the PCB, we don't want to go into the keep out zone. The keep out zone is basically there because the ESP32 has this antenna on top, and this antenna like basically wants to have free space around it so that it works properly. Okay, there's like theoretically there's no reason not to extend the board further, but you can't do anything with the extended part of the board because like you can't have copper there. If you have copper there, it interferes with the electromagnetic properties of the antenna. So we just end the PCB here. Fair enough? Okay, but we can play with the other two sides of the PCB. So like I can just make this as big. Oh shit! I can make this as big as I want, as long as I don't change like the left and top side. Okay. All right.
Wait, can I make this like a rectangle with a hole in the middle for the two bus?
I think you can just put a hole like this and then like. Oh, why? So I have to do a fill.
Yeah, I think so. You have to fill it.
Okay. He asked, can I put a hole in the board? I genuinely don't know how to put a hole in the board. I've never had to do it before. Penny, how do I put a hole in the board? No, not mounting hole, like a slot or something. So I just do this. Is that it? That's the not that because that's broken, but this is fine, is it?
Like slots or
Oh, it was that easy. Oh, I was just in the wrong layer. I was in fabrication layer. That's why it didn't work. Yeah. Okay. So yeah, I guess you can just put a huge hole here if you wanted to. Yeah.
So, fillet your corner, like, fillet, you don't draw the rectangle.
Fine. I'll fillet the corner. Huh?
That's the center of the corner. Put the center, like, inside the, yeah.
Like this?
Right, no, yeah, then you,
I'm supposed to do this?
yeah.
This is such a painful way to fillet thing. Oh.
Like that, yeah.
Then-
Snap to 90, but
then
you
how
have to
do-
use, you cannot use rectangle, you have to use line. Then just line plus the two radius.
Alright, so basically it's too much effort to fillet the board lah. I'm not filleting the board. Okay,
That's insane.
no, it's fine. Everything is fine. What was I about to say? Oh yes, okay. So everyone's 3.3 volt and ground is not connected right now, right? No problem. I'll show you. So right now everything is on the top layer. I'm gonna hide fabrication again. So I got all this redness saying, "Hey bro, you haven't connected a bunch of stuff." Go to field zones. Okay, click it. Now draw the bounding box. So you click first and then you choose the net. Okay. Okay, what we're doing is we're applying an area of copper. And this area of copper is going to avoid everything which is not part of its net, and it's going to connect to everything which is part of its net. So it's going to... For now, never mind. Okay, you'll visualize it in a second. Choose ground. Okay, choose ground.
How did you get there again?
Okay, go to field areas here. Then click any point. I mean, not any point lah. Actually, it'll be like one of the corners of wherever you want to fill. And then click ground as the net. Is anyone stuck? You guys, are you guys able to find guys, you need to be on a copper layer. Yeah, go to the front copper layer because that's where all our parts are. Okay. So front copper layer, then click ground. Okay, now we're going to draw a bounding box like this. 1, 2, 3, and on the last point we double click. Okay. So now look, I've got this kind of like serrated bounding box. Have I lost anyone? I've got this serrated bounding box. Now I'm gonna press B. This is an entire zone of copper, and check it out, it's wiring all the grounds together for me. So this is called a copper pour, like I pour a liquid, okay? And it's connecting all of these grounds together, and this is basically like the widest possible trace that like we could theoretically fill the space with, connecting everything together, right? And it's connecting with these like spokes, which we call thermal relief. Okay, so it doesn't just fuse all the way, it actually connects with thermal relief on the pad connection. And what that does is we don't have too strong of a copper connection, because if the copper connection is too good, then this will act like a heat sink, and when we try and solder this, all the heat will fly away from the pad and we can't solder anything. It will just dissipate into this giant copper area. Okay, so this is a thermal property of the board, and thermal management is the thing we'll talk about next lesson. Okay, but for now, just know that like, yes, things get hot, and like sometimes things are supposed to be hot, and like we think about it next lesson. Okay, okay, check it out. We still have a rat's nest. This is my 3.3 volt line. Also check it out. This part of the copper pour, this part is completely not connected to this part of the copper pour. See, like it can't get past this area. It can't get past this area. So even though there's a ground connection here and here, these are not really connected to this. At least not on this side. It's connected like the long way. It's connected like this, right?
That's what the shielding of the electrode is for. The shielding makes sense. Oh, but yeah, never mind.
Okay, so in our application, it's managed to connect from the other side, so we're fine. Okay, but sometimes you will have a copper pour and it will just fail to go through some areas. So you need to understand that a copper pour doesn't magically just connect things. Sometimes it has an obstacle and it just can't get through. Okay, so it's up to you to check whether your copper pour is actually connecting stuff together. Okay. Any questions about copper pours?
Let's say 3.3.
Yeah. Okay. Okay. Yeah. So so now we're gonna talk about multiple layers. Okay. So this whole time we've been routing stuff on the top layer, the red layer only. But we can route stuff on the bottom layer as well. Okay, I'm gonna Control B to unfill my copper pour. Okay, and this is so that's easier to work with. Control B. Okay, so B will fill my copper pour. Control B will unfill. Okay, so I can route this together, 3.3 volts. I'm gonna route this out to like some location in space. I don't care where right now. I go to VR. Place VR. Okay, a VR is a connection between layers. Okay. So basically what they've done is they drill a hole through your board and then they coat the walls of that hole with copper. And now it's like a vertical tube-shaped wire connecting your two layers. That's what a VR is, okay? So I can place the VR and it looks like this. And if I zoom in on the VR, it tells me what net it's a part of, which is nice, you know? So I can do this here and I can do this here. So route this out. Oh, actually let me use a fat trace because I might as well. Route this out and use a VR like that. Okay. Now I can go to the bottom layer. Check it out. On the bottom layer, my VR is now blue. On my front layer it's red. On the bottom layer is blue. So basically what we're doing is we're rendering the bottom layer in front of the top layer instead of vice versa, right? So that's why it turns blue instead. Now I can have a blue trace. I can have a blue trace and it can cross over my red. It can cross over my red with no problem because it's on a different layer. It's fine, right? Does this make sense to everyone? What we're doing? So this is how we cross wires over each other. If we only had one layer, this would be impossible. So we have more than one layer, and now we can just have wires on different layers, and then now they can cross over each other, and we can have much more flexibility with wiring things. Make sense?
When we do this, do we have to be like careful of like impedance?
I mean, for power, usually you're okay. You need a low impedance connection from the decoupling capacitor to the IC. The IC being like the ESP or like literally anything. IC means integrated circuit. Okay, so like a chip basically. So that needs a decoupling capacitor, right? Anything that draws power needs a decoupling capacitor. But other than that, you just make it low impedance and you're fine. So that means like have a nice wide trace, you know. Make sure that your current capacity is good enough. So let's say the microcontroller is going to draw 600 milliamps. make sure your trace is at least like wide enough for that, you know. And then like spike current being 2 amps, then like make sure your trace is okay with that, you know. Like online calculator will save you. Okay.
Yeah, but no, this thing is, I was thinking like this kind of thing shouldn't there be like, well, someone should have developed like software that you just highlight the whole thing, click a button, and then you automatically.
Yes, but impedance management at high frequency is a nightmare, and like the software problem is insane. So like nobody has done that. You can auto route something like this with a software and like it'll work, but like if the moment you have high frequency, it's over. Yeah. Yeah.
But like, okay, let's say I do want to do like just a simple thing. It's just a simple one. How can
I think you can literally right click it.
Oh.
Maybe this one. I don't know. I don't know how the menu works.
Oh.
Does anyone have any questions? It's not ideal, but it's okay. It means that whatever current that wants to flow back to the power supply ground cannot take the short path and take it. This can be a problem at times, but on top of that, that's just, it's not going to affect anything.
So it's like it will become like more polarized.
High frequency. Yes. It's very easy. It's very easy.
Yeah, that's right.
Okay, so once we routed our stuff, we can just press B again to route to like fill the copper pore. Alright, so now we have our board, right? My board looks ridiculous because but like we can just make it smaller. This is fine. Okay, great. So looks like I have no more rat's nest. Okay, so I should have routed everything already. I'm gonna press Ctrl S reflexively. But like there's this button here with a tick mark on it. Design row checker. Click it and press click all, like check everything basically, and then press run DRC. Okay, the design row checker is a software which tells you if there's something wrong with your board. Okay, it's not going to check for impedance problems, but it will tell you if you forgot to connect something, or if something is like intersecting something else. Okay. So for example, it's complaining that my silk screen is interfering with the edge of my board. There's nothing I can do about this because the silk screen just extends out, like for the ESP32 antenna. Okay, but then what about this? Same thing. Hole size out of range. Okay, nobody cares. Yes. Okay, so we'll go through some of these errors, but like don't stress about them too much. Okay, hole size out of range basically says that look, this is a VR and it's too small. Okay, so the ESP32 has a bunch of VRs in the middle of it. This is a thermal reason. Okay, so if I hide this again, this is a grounded pad, and when I go to the other side, it's got VRs as well. So what this is trying to do is conduct heat away from the center of the ESP32 and to the other side of the board. So ideally, on the other side of the board, I also put a ground pore like this. And the ground pore is going to act like a big heat sink for the ESP32. Okay, so this is like kind of non-critical, but it helps. So now on the back of my board, I've got this big heat sink. So heat will conduct from the center of the ESP32. It will radiate out to the front ground plane, and also go through the VRs and radiate out the back. So this improves our thermal performance. So when we put VRs specifically to conduct heat, we call them thermal VRs. electrically they work exactly the same as regular vias. We're just using them for a different reason. Okay, so these are thermal vias, and in this case they're all like too small, so the diameter should be 0.3 whatever. Okay, so smaller vias are more expensive to produce. 0.3 is the standard, 0.2 is expensive. Okay, so if I run DRC again, you notice that the via which I expanded no longer has a red arrow on it, so it's no longer a problem. So we can set our default minimum via size in like the board settings somewhere. Out of scope for the lesson, frankly. It's not that important. You can Google how to do it. Okay. Okay. We wanted to talk about MOSFETs and some other stuff during this lesson, but I think we'll just overflow that to the next lesson. Okay, that's absolutely fine. The important thing today is that we taught you hands-on skills and we actually wired something, which is important. Okay, so this ESP32 is lacking a power connection right now, but once we add the power, it should work already. Okay, this thing will actually run and be a functioning dev board. We just need to add some like headers to it so that we can plug shit into it basically. Okay, so we made good progress today. Joseph, I ran out of content. We'll move MOSFETs to the next lesson. Yeah, cause we're out of time. Yeah, I showed them DRC and that's the last thing lor. Yeah, is there anything else that we said we'd show? Nah, we're good. Yeah. Yeah, all the other stuff we'll show next lesson.
Wait, can I put a via directly on the component?
Yes, but that's okay. So let's say here I just put a via like right here, right?
Yeah.
Okay, so when you put a via like right in the middle of a pad, we call this via in pad. Okay, via in pad requires special considerations because remember a via is a tube, and then I drill a hole and then I coat it in copper, so it's like a tube shaped copper. So if I put that in the middle of a pad, then when I try and solder the pad, the solder will like flow into the tube instead of like soldering properly. So this will cause soldering issues. So via in pad technology caps the via off with copper, so that like it's not a tube anymore, and like now the solder cannot run away. But this is an expensive process. So generally we avoid using via in pad. We always route out, and then we put a via outside the pad, and this avoids that problem. Okay?
Okay, wait, hang on. Did you say something about how to name a via?
I said that when you zoom into a via, it will tell you what net it's connected to.
Yeah.
Yeah.
Oh, what are you doing?
Trying to make this one to this test.
Okay, then you just connect.
They won't let me.
And then let's
So for the purposes of this course, we're only going to put all the components on the front side, because that means that if you ask the company to solder for you, it will be cheaper. If you do both sides, it's very expensive because you cannot use economic assembly. You use standard.
Oh, there we go.
Yeah, economic assembly only allows you to assemble one side. Also, we're probably gonna do we didn't include it in like the curriculum, but we'll do a hands-on lesson at some point about how to solder. So that means like regular soldering, also PCB soldering. We have the tools and equipment for that, so we'll teach you guys those if you want. And then like it's just easier to use one side only. Because like if you got both sides, then like you try and solder one side, the other side stuff dropping off. It's very annoying. Yeah. I mean,
because of the service tension or something.
Yes lah, but also like, you know.
Just those skill issue.
Yeah, you might as well.
Honestly, the biggest danger is just overheating the component and frying it. Okay, then that's all for this class, and we'll overflow everything else for next class. Because like, I also have other things I need to do. Yeah.
Yes. I was thinking of like this image of somebody putting this soldering.
Iron to sell.
Yeah. That's it. Oh, you didn't even use it?
Oh yeah, am I supposed to?
You don't have to.
Oh.
You can actually do this, but you can press B and then it will go for you.
Oh, but why would I?
It's lower the difference.
Oh, ground needs to be. Oh.
Yeah. So basically, I mean, we'll go through it harder. We'll go through it more in lesson steps. Like ground should be low.
Oh yeah, that makes sense.
So you can be and control it because those like until and
Okay, yeah, it makes sense because you want ground to be like zero, so like you just dump the electricity into the middle of buckets now.
Yeah. I think that's what you want to do. It's essentially
Okay, yeah, how did I not think of that? That's why you asked us to pour the ground. I was like, why are we pouring? You're spreading the electricity everywhere.
no, but that's fine actually.
Yeah, that's the point of ground. My brain is now braining. Ah,
No,
okay,
it's fine.
okay.
It's fine. Actually, there's nothing wrong with using
Wire.
cores for power as well. There's really nothing wrong with it. It's just that usually you don't need it.
Just you want the power to be like everywhere across the board. You just stick to it and you should have the
Yeah, because like when you have a whole plane which is ground, you just fear down into it. Like so like when you have like multiple layers, then it's very useful instead of routing things, you just fear all the way down.
to the ground.
Exactly.
Yeah, so we have like 4 layers, power layer, ground layer, wiring layer, and backlight. Also
Yes, that's quite a common structure. Yeah. Actually, we'll go through like so that's fine, but like we'll go through like better examples of like what good PLD is. So usually it's much more beneficial to do signal ground signal, and then power is just ground. And this is for like it's for funny reasons. They're actually shortened together. They're still the same ground.
Oh,
It's just that lesson 7 will be talking a lot about when ground no longer becomes ground. When like suddenly ground is 0.1 volts or like some funny thing like that. Or like we'll talk about like shielding and coupling and like crosstalk and how to like basically ground solves like 99% of problems with like interference. You just have ground everywhere. But then like it's very weird. That's why there's a whole lesson.
understand. Alright, thanks, man. Alright, nice. This is. I'm very happy with what I did.
Even though the 16 switches are
Oh, this is a key. It's not easy.
this is a different course. This is a
Where are you going after this? You have to go somewhere, right?
Wait, who borrowed me the charger?
I think spending. Oh, it's spending. Okay.
Where are you from? You're from GC.
I did this one the whole reason because even before overseas exercise, go over it and
Check.
if I could bring a laptop, I did this.
You are how come you cannot bring that back? Or like your OC just
You take out this thing like
the last 2 months.
oh,
When this bring out once.
seriously.
Yeah, but wait, where is it?
Not my one for
That's Pokemon. Are you staying?
I should pay one house on there, but look at it. I know. This was actually so much fun. It did take me like 3 hours, but it was so much fun.
It's
Housework. Tiring. I can tell like you're very tired today, even though you didn't work. Are you okay?
Are they
no, not one point. Are they switches?
Oh,
Yeah, it's like single switch is just like
Okay, yeah, that's all we have for today. Can yeah.
What a day. Why am I so
No problem.
productive
Hope it was
today?
useful, and next lesson we'll do better. Huh? Penny, I just stopped screaming, right? I don't have to do anything.
give an outro.